Good afternoon. This is the pre-dispatch demonstration video of the Frey Analgesiometer, the digital Frey Analgesiometer, or also called the dynamic Plantar Aesthesiometer. So the Frey Analgesiometer has on the top a acrylic cage for rats. This cage has already been assembled for the inspection purpose. As you can see, it actually comes in a dismantled form. It has been assembled here for the demonstration. It has 4 walls which are held together by these bolts, and the vertical walls, they are inserted into slots, as you can see. So there are 1 2 3 4 5 walls which give you 1 2 3 4 5 and 6 cages for normal sized rats. And if we remove this wall and every other wall, what we get is 3 cages, number 1, number 2, number 3, for very large sized rats or fat rats. And as you can see, there are also slots perpendicular to these walls, and we have here some more acrylic walls which can be inserted into those slots, and then we can work with a total of 12 mice. So 1 2 3 4 5 6 7 8 9 10 11 12 mice in total can be had here. This table or this platform which you can see is SS304 high quality platform. It has a perforated SS base so that the probe can enter from underneath and be touched upon the plantar surface of the paw of the animal. Here we have the touchscreen control system, from which we will be able to control the motion and the rate of climb or descent of the probe. It is in mm per second. So we can increase it by 1 value or by 0.1 value. So either by 1 or by 0.1 we can increase or decrease this. So this is how this works. Here we are getting the readings in grams force which the sensor is giving. The sensor is very sensitive, so it is able to measure even a hundredth of gram of force, which generally comes even from slight vibrations in the on the table or in the environment, or coming from any sources. Here we can do the sensor selection. We have actually 2 sensors here. This is a 50 gram force dynamic force transducer, and we also have a 1000 gram force or 1 kg dynamic force transducer. So depending on what transducer we are using, we can do the selection here, either 100 grams or we can go to 1 kg. Now this is the main part of the instrument. This is a dynamic touch simulator. So what this does here is that we have a platform here, and this platform, based on what speed we have decided here, can be raised up or descended down in that rate of speed. So suppose we want a very gentle touch on the plantar surface, we will set the speed here, let's say about 1 mm per second. We will set the speed here and place our let us now place the transducer here. We can place the transducer here through the guides, and the transducer is now ready to work. What we need now is the probes. So we will first take the transducer out, and on the transducer we will have to mount the probe. So this is the probe mount. It has a lower slip lock on the top, and attaching a probe is very easy. What we do is we first select our probe. We have many options, 4 options to be exact. There is the 1 mm probe, then there is the 0.6 mm probe, then we have the 0.8 mm probe, and we also have the 0.4 mm probe. Now suppose we have chosen the 1 mm probe. What we will do is we will take the probe out and we will attach the probe to the slip lock. Just push it in and the probe is now attached. It has a blunt tip, so this is not sharp, this will not hurt the animal, but the diameter is, as we have decided, 0.1 mm, and just gently put it here. Now this surface is a very sensitive surface. We are not to put any pressure on this. While attaching the probe or while removing the probe, we have to take this out and then work with the probe, and just drop it here when we are ready to work with it. That's it. Now this is a 100-gram dynamic force transducer. This is even more sensitive. This is a 50-gram dynamic force sensor, so we have to be even gentler. We cannot lean over it or put pressure over it. That is not to be done. Just leave it here and now we can work. And when not required, just take it out, or when we want to change the probe, just take it out. Now we attach the probe here and we can now shift this to the force transducer. Very careful that we do not bump the probe on the top of the surface. Just gently slide it in. That is all which is required. And now we can observe how we are working with the probe. Now as you can see, our probe is in alignment and the animal will be somewhere on the upper side of the mesh, and we have to manually align the probe with the hole on the mesh over which the plantar surface is located. We have to visually inspect that spot, and this over here we have a pedal switch. This will be on the floor, so researcher can just put it on his under his foot and just press the button and the surface will rise at the set rate. Now we are not at the hole, so we will align this a little so that we are underneath a hole. Now we are there. Now this is well aligned, and now we can further raise this. At 1 mm per second, this is rising now. You can see here that the probe has come out of the hole, and if there was the foot of the animal over here, we would have taken a measurement. This measurement is being continuously sent to the LabMonitor desktop software, which will, once again, let us now so here you can see we have raised this sufficiently so that this is easily visible on the camera. The probe has come out of the perforation, and if the plantar surface was over it, it would have taken a recording of the force being applied on the plantar surface, and then that data is being continuously sent to the desktop software, which is the LabMonitor software, and there the graph will be plotted for the force, and the moment the force applied is the force significantly drops, that is the moment when we know that the animal has lifted its lifted its limb, because it could not tolerate the force anymore. And that is the point at which the recording will be taken, that what was the force at that point, and we can save it in PDF and Excel. That is entirely the function of the software, that is not the function of the hardware, and it will be exportable in PDF and Excel. Thank you.